Okay, in the last lecture, we have discussed the concept of the absolute convergence series, conditionally convergent series, and also we have discussed the grouping of the series and rearrangement of the series. So, grouping of the series we mean if a series is given sigma x n of real numbers n is say 1 to infinity as series. Now, if with the help of this, if we construct another series sigma by n is 1 to infinity, where the terms of the series, order of the terms of the series are is kept fixed. We are not disturbing the order, the first element remain in the first place, second element remain in the second place, but what we are doing, we are grouping the finite number of terms, and then the new series so obtained will be known as the series grouping or grouped series of the previous one. And in that case, we have also seen a result that if a series sigma x n is convergent and has the sum s, then the corresponding grouped series will also be a convergent series and will have the same sum as the sum. It means, by grouping the terms of the series, the new series so obtained will not change its character. If the original series is convergent, the newly constructed series by grouping the elements will also be convergent and the sum will remain the same. So, this is the case of the grouping. Okay. But in case of the rearrangement of the series, rearrangement we have defined like this: rearrangement of series. Suppose a series is given sigma x n is 1 to infinity, where x 1 plus x 2 plus x n and so on. And if we construct a series, another series by n from the given series x 1, such that we are using all the terms of the series only once, by using all the terms exactly once, but scrambling the series obtained from the given series say 1 from the given series by obtained from the given series by using all of the terms exactly once, but scrambling the order in which the terms are taken. So, the series obtained from the given series 1 by using all of the terms exactly once, but scrambling the order in which the terms are taken is known as rearranged series. So, in this case, we are free to interchange the position of the terms and then taking the new series and then considering the new series so obtained. Now, as in the case of the earlier, when grouping of the series does not change the nature of the series, but in case of the rearrangement of the series, the nature is may change, even the sum changes. If the series is convergent having the sum s, then if after rearranging the terms, the series will remain convergent, but the sum may differ. So, this was observed by Riemann, and the Riemann basically this is the Riemann observation. What Riemann has observed, what he says is the observation, if the series sigma x n is 1 to infinity is a conditionally convergent series is conditionally convergent in R set of real numbers, of course, a series of real numbers, and if C is any point real number belongs to R, say is arbitrary, then there is a rearrangement of the series sigma x n of the series that converges to C. So, this was the observation made by Riemann. It means, if a series is not absolutely convergent series, but it is a say conditionally convergent series having infinitely many positive and infinitely many negative terms, then in that case if I rearrange the terms of the series and gets another series, then such a series can be will have a sum different from the previous one. In fact, if I want a sum to be C, then an arrangement can be possible, so that the rearranged series will converge to the value C. And this observation can be justified by Riemann is justified like this, that first the condition is the series should be conditionally convergent. Second condition which he has imposed is there should be infinite number of positive terms, infinite number of negative terms, and then what he did is he first considered the first positive terms whose sum positive terms, and the sum of that series of the positive terms does not converging to does not exceed y greater than C, sum of the positive term greater than C. Then later on he considered the sum of the negative terms which are greater than C, and like this he is able to show that for any given C one can make a rearrangement, so that the series will converge to the same point C. So, this was the observation. Now, if such a series is given which is conditionally convergent, but not absolutely convergent, then obviously the series will give problem when we interchange or when we shifting the position of the points, that is the terms are shifted or interchanged, then you will not get the unique sum. However, this case is not there in absolutely convergent series. So, this next result shows if a series is an absolutely convergent series, then whatever the rearrangement we made, the series will remain convergent and will have the same sum as the original one. So, this result is given in the form of theorem which is known as the rearrangement theorem. Rearrangement theorem. The theorem says like this: let sigma x n 1 to infinity be an absolutely convergent series, absolutely convergent series in R, then any arrangement sigma by k 1 to infinity of sigma x n converges to the same value see the proof of this. So, this is very interesting result, that if you are dealing with the absolutely convergent series, then we need not to bother in that the rearrangement of the series will give the different sum. It will not give the it will give the same value as the previous one earlier. So, suppose the series sigma x n 1 to infinity is convergent series and converges to the value say x belongs to R. So, by definition if the series is convergent, then sequence of its partial sum will go to x when n is sufficiently large. So, for a given epsilon r greater than 0, there exists a positive integer capital N such that when n and q both are greater than n and the S n be the sequence be partial sum, sequence of the partial sum say x 1 plus x 2 plus x n, sum of the first n terms of the series, then the x minus S n is less than epsilon r, and sigma of this mod of x k when k varies from n plus 1 to q remains less than epsilon. That is, if the series converges, then by definition sequence of its partial sum will go to 0. It means the remainder terms of the series will remain less than epsilon. So, for any q which is greater than k, this is the basically the first remainder terms where finite terms from the remaining series, it will remain less than epsilon. Okay. So, this is true. Now, let us take the rearrangement of the series. Let sigma by k is 1 to infinity be the rearrangement of this series sigma x n, with the rearrangement of this series sigma x n. Okay. Now, if I choose let m belongs to the positive natural number, this is the a positive natural number capital N, and here is the capital N is just a some positive integer n. So, set of this natural number. So, capital M is a positive integer capital M be such that all the terms say x 1, x 2, x n are contained in say T m summoned by 1 plus by 2 plus by m. This is a rearranged series, and what I am doing is I am taking the sum of the first m terms. Since it is a rearrangement, it means we are just changing the order of x 1, x 2, x n, and the new series is so obtained, but the first m terms which we are choosing involves this x 1, x 2, x n plus few more terms of course, is there in that. Okay. So, obviously, it follows. So, obviously, when m is greater than n. So, if m is greater than or equal to m, then in that case the T m this sum minus S n, because this sum will definitely involve x 1, x 2, x n. So, when you take the minus, so x 1, x 2, x n will go out, and this will be is a sum of finite number terms x k is the sum of finite number of terms x k with k x k with k greater than capital N, because those x 1, x 2, x n will get cancelled, and since m is greater than m and this sum contains all x 1, x 2, x n. So, those terms will vanish, will cancelled, and the remaining term will definitely start from n onward. So, this is x k when k is greater than n, like this. Okay. So, this will be there. Hence, for some q, therefore, hence for some q which is greater than n, we have T m minus S n, T m minus S n mod of this. Now, this will remain less than equal to sigma k equal to n plus 1 to q mod of x k, because T m minus S n will involve those term x k when k is greater than n. So, we can find the q such that this sum of these terms will remain less than or equal to sigma of this, but because the series sigma x n is a convergent series. So, this condition holds. So, this will remain less than epsilon r. Okay. So, this will be less than. Now, we wanted that the series sigma by m is convergent. We want this series to be convergent, converges to the sum x. So, let us find the T m minus x, x is the. So, consider, so if m is greater than equal to m, then consider mod of T m minus x. Now, this will be remain less than equal to mod of T m minus S n plus mod of S n minus x. Now, T m minus S n is already less than epsilon r. So, this is less than epsilon r and x is the sum of the series. So, S n will go to x. So, this will remain as the epsilon r for all n m greater than equal to m. So, this is true to S m, but epsilon r is arbitrarily small. So, when this shows when epsilon tends to 0, this T m will go to x. Therefore, this implies the series converges sigma by k, k is 1 to infinity, converges to x. So, that proves the result that in case of the absolutely convergent series, the rearranged series so obtained will remain the convergent and will have the same sum as the original one. Okay. So, we are mostly interested in those series which are absolutely convergent, because the nature of the series if it is convergent, then we need not to bother for the rearranged series, because whatever the way you sum up, the sum will remain the same. So, let us go for the some few tests for the absolutely convergent series. So, test for absolutely convergent series. Okay. Absolutely convergent series. We have already seen so many tests for a convergence of series of real numbers, and one condition for this is comparison test we have seen, nth root test we have seen, and then Cauchy convergence criteria is also there for the convergence of the series and like. So, here we will simply state the few results without proof, because the proof runs on the same lines as we have done earlier for a general case. Okay. So, let us see the first result says, which is the limit comparison test. Comparison test. First one we have seen, this is the second test. We are saying what it says, suppose that a series, a sequence x equal to x n and y equal to y n are non-zero real sequences and suppose limit of this exists, limit of mod x n over by n say is equal to R exist in R. Then what is result says, if R is different from 0, if R, then the series sigma x n 1 to infinity is absolutely convergent, if and only if the series sigma by n is absolutely convergent. And second result says that if R is 0 and if the series sigma by n is absolutely convergent, then the series sigma x n is absolutely convergent. So, this what this says is, suppose the two series are given, one is the sigma x n, other one is the sigma by n. The result says, if x n by n both are sequence of real numbers, and if this limit x n over y n as n tends to infinity, limit of this exists, and suppose it is R, then the R, if it is different from 0, then nature of this series sigma x n and nature of this series will be the same. So, for the absolute convergence is there. That is, if a series sigma x n is absolutely convergent, then sigma y n is absolutely convergent and vice versa. Now, if R is 0, then in that case sigma x y n is absolutely convergent will imply the sigma x n is absolutely convergent, okay, but not the other way around, Okay. So, just given series, if we are able to construct the series by n in such a way, so that the ratio limit of the ratio exists, then one can identify whether the series is absolutely convergent or not. Okay. This is the one. Then another test is, I think examples we have already seen. Suppose I take a series sigma 1 by n square, say suppose, okay, then 1 by n square, and if you take another series say n plus 1, say for example, if I take the sigma 1 by n plus 1, say 1 to infinity, we want this series to be testing this series, all the terms are positive of course. Then what we do, construct the sigma 1 by n square, this is equivalent to sigma y n, this is equivalent to sigma x n 1 to infinity. Okay. Now, this series, nature of this series we know, it is a convergent series, because of sigma 1 by n to the power p. Now, what happens if we take the x n, the same x n over by n mod of this, limit of this as n tends to infinity. What is this? This limit is nothing but what? N square over n plus 1, limit as n tends to infinity. So, if I take n outside, then we get basically the limit is 1 different from 0. So, here R is different from 0. Therefore, both the series will have the same nature. So, this series is absolutely convergent, therefore, this is also absolutely convergent. Okay. So, that way we can find. Similarly, for the R is 0, we can get it. The second test, which is root and ratio test, which is the root test. Let x, which is say x n, be a sequence in R, be a sequence in R, a number. Then first, if there exists R, if there exists R in the set of real number, means R is a real numbers with R less than 1 and a positive integer k belongs to set of natural number n such that mod of x n to the power 1 by n, mod of x n to the power 1 by n, this mod is less than equal to R for n greater than equal to k. Maybe the few terms this condition may not be satisfied, but after a certain stage the mod x n to the power 1 by n remains less than that number R, which is less than 1. Then the series sigma x n 1 to infinity is absolutely convergent, This is one. And second word, if there exists k, if there exists a positive integer k greater than 1, belongs to n, of course, k belongs to n, positive integer, I will say positive integer k, belongs to n such that, maybe equal also, there is no problem, okay. K belongs to n such that, or you can remove this, there exists a positive integer k such that mod of x n power 1 by n is greater than equal to 1 after this n greater than or equal to k. Then the series sigma x n is divergent. So, again this is the nth root test, is the parallel to our root test for general sigma x n, when go mod of x n to the power 1 by n r, if lying between 0 and 1, then this is convergent, greater than 1, then diverges, is it not. So, mod x n is greater than r is strictly less than 1. So, again this proof will be the same. So, we are just dropping. Now, since as a corollary of this, in earlier case also we have seen the limiting, instead of choosing, because this inequality to identify such an R is a difficult one. So, what we do, we wanted to avoid this part. So, instead of this we can take the limiting value, and as a corollary we can say of this result is, let x, which is x n, be a sequence in R, and suppose that the limit of this x n mod x n to the power 1 by n as n tends to infinity exists n equal to R in R exists, then the series sigma x n is absolutely convergent. When R is strictly less than 1 and is divergent when R is greater than 1. So, for R is equal to 1, we cannot say anything about it, because if we take the sigma 1 by n, then R is 1, series diverges. If I take sigma 1 by n square, then also R is 1, but the series converges. So, for R equal to 1, conclusion cannot be drawn, is it. So, this one. Now, then is next says also this is the root test, ratio test. Third test is ratio test. Let x, which is x n, be a sequence of non-zero real number. Real numbers. Then the first says, if there exists an R, if there exists R belongs to the set of real number capital R with 0 less than R less than 1 and k belongs to n set of natural number n such that mod of x n plus 1 by x n, this is less than equal to R for n greater than equal to k, then the series sigma x n 1 to infinity is absolutely convergent. And part B says, if there exists k belongs to the set of natural number n such that mod of x n plus 1 by x n is greater than or equal to 1 for n greater than equal to k onward, then the series sigma x n 1 to infinity is divergent. Again, as a corollary of this result is the limiting variable. So, again we say the corollary to this is, let x n be a sequence of non-zero terms. If x n be a non-zero sequence of real numbers, and suppose that the limit exists, limit of mod x n plus 1 over x n as n tends to infinity exists and say R, then the series sigma x n 1 to infinity is absolutely convergent when R is strictly less than 1 and is divergent when R is strictly greater than 1. Again, for R is equal to 1, test fails. Okay. So, now if we look this thing, then for R equal to 1, the testing fails. Okay. Now, there is another test which is known as the integral test and which is very powerful test, but of course, it requires a knowledge of the Riemann integral function, but here we will assume f is an element in the Riemann integrable function. Riemann integrable function we mean that suppose a b is an interval. Okay. A b is an interval, say here when we divide this a b into the partition and then finding the sum of this, then a to b f d a can be written as the limit of the sum of this. So, this we will discuss it when we go for the Riemann integral chapter on Riemann integration. But let us assume the f is an element of the Riemann class of Riemann integrable functions, where the integral test. So, we are interested in the test right now. So, third test is, or fourth is the integrals test, which is very powerful test. Okay. So, here we assume let f be a positive. Now, one more thing is concept of the improper integral. So, here let f is an element, or let us take what, let f be a positive decreasing function on the set T, where the T is greater than or equal to 1. Then the series sigma f k, k is 1 to infinity, converges if and only if the improper integral improper integral 1 to infinity f t dt, if the improper integral which is limit 1 to b f t dt b tends to infinity exist. Okay. In case of the convergence, the partial sum S n of the series sigma f k, k is 1 to n, the partial sum is k is 1 to n, k is 1 to n f k, and this is k, okay, and the integral and partial sum this and the sum s and the sum s, which is sigma f k, k is 1 to infinity, satisfy the estimates the inequality integral n plus 1 to infinity f t dt, which is less than equal to s minus s n, which is less than equal to n to infinity f t dt. So, what this result says is that if f be a positive decreasing functions on this interval, on this set t, where t is greater than equal to 1, the series sigma f k converges if and only the corresponding improper integral exists. So, basically the integral sets test, it connects the convergence of the series, infinite series, with the improper integral. So, here we are having the two terms, one is the improper integrals, another one is the of course, that Riemann integrable functions. Now, what is this improper integral? Let me, before going for the proof, let me see the first, the improper integral. Improper integral. Improper integral is, if suppose the function f which is defined over a certain interval say a b, then a to b f t dt. If f is a continuous function, then this integral is known as the definite integral, which we know definite integral, is it not? If f is a continuous function, then a to b f t dt represents the definite integral, and it is known as the definite integral, and it represents the area bounded by the upper bounded by the function y equal to f t and below by x axis and a to b two ordinates. Now, if one of the limits is infinity or minus infinity, then such an integral we call it as an improper integral of the first kind. If either a or b or maybe both, one of the limit either a or b is plus infinity, minus infinity or maybe both, then the integral is known as improper integral of first kind. Now, once we have one of the limit as improper integral, that is integral a to infinity f t dt. So, this is improper integral of the first kind. Now, whether this integral converges or diverges depends on the limit of this. What we do is we consider a to b f t dt and then take the limit v tends to infinity. Now, if this limit exists, then we say this improper integral converges. Now, if this limit does not exist, then we say this improper integral diverges. Similarly, minus infinity to alpha, we can in a similar way we can say define the convergence or the divergence of this improper. The improper integral of the second kind are if a and b f t dt is given, but f is not continuous. Suppose it has a point of discontinuity over the interval a b, then such an integral is not defined basically over the whole interval a b. Say for example, if I take the improper a to or 0 minus 1 to 1 dx by x. Now, this integral function f x is 1 by x is not defined at x equal to 0. So, it is an improper integral of second kind. Clear? So, these two types of improper integrals are, one is the improper integral of first kind, another is the improper integral of second kind. Now, here what we are assuming is improper integral of the first kind. So, if a series is given and the function f is such which is of decreasing nature over the interval 1 to infinity, then the nature of this series sigma f k converges if the corresponding improper integral will exist. Clear? And of course, vice versa corresponding. So, this rates the convergence of the series with the improper integral, and that is why it is known as the integral test. It is very powerful test, one can derive the earlier test with the help of this integral test. So, let us see the proof of this result. So, we go to the proof of this. Okay. Now, it is given that function is decreasing since f is positive and it is of decreasing nature and decreasing on the interval over the interval t is greater than or equal to over this set. So, we can take the interval say k minus 1 k. This is interval function is decreasing over this interval k minus 1. Then we have obviously this relation that f of k is less than or equal to integral k minus 1 to k f t dt, which is less than or equal to f of k minus 1. Since the function is decreasing, the largest value will be attained at this point k minus 1 and lowest value will be attained at the point f k. What is this value? This is the area represented by this. So, basically the functional value between k minus 1 to k. So, this will be the portion in between these two. Okay. Now, let us take the sum. So, take the sum of this, take sum over k when varies from 2, 3 say up to n. Then what happen? When you take the sum of this k, then it is sigma k equal to 1 to n is the S n. So, we can say S n minus the first term f 1, right hand side, and this is k equal to 2, 3. So, 1 to n f t d t, which is less than equal to, when you write the sum of this, it is S n minus 1. Okay. So, we get this. Now, from here say star, what we say, the nature of this limit of this integral will depend on the limit of S n and vice versa. If the limit of S n exists, the limit of this will also exist. If limit of this exists, limit of S n will also exist. So, this shows that this implies the both or neither of the limits exist, both or neither of the limits S n as n tends to infinity and limit as n tends to infinity 1 to n f t d t, both will exist or both will not exist. That is one thing which you. Now, if they exist, then add them. So, then add this say this part from here again, let it be a, then sum is a for k is equal to n plus 1 to m, where m is greater than n, sum of this. So, when you sum up this thing, what happen? This is k equal to m to, so S m minus S n. So, this will give S m minus S n, which is less than equal to n to m and f t d t, which is less than equal to, again when you sum up this thing, that will be equal to S m minus 1 minus S n minus 1. So, that will be there. Okay. Now, from here, so this implies that. Now, if I take m integral of this, say suppose I replace n by n plus 1, m by n plus 1, then what we get? N plus 1 to m plus 1 f t d t. This is nothing but what? When you write m equal to m plus 1, n equal to n plus 1, this is less than equal to S m minus S n. But S m minus S n is also less than equal to this integral n m f t d t. Okay. Now, clear? Now, from here take the limit as m tends to infinity. So, take the limit when m tends to infinity, fix n by fixing n we are not touching. Then what happens? When you are taking the limit, you are getting n plus 1 to infinity f t d t. F t d t is less than, when m is sufficient, this will go to S. So, S minus S n, this is less than equal to n to infinity f t d t, and that is what the result says. The result is this, is it not? So, we got the result for it. Okay. So, this proves that. Now, let us say application part. Suppose I take how to apply of this result. Let us take this series. We know the series sigma 1 by n to the power p 1 to infinity converges if p is strictly greater than 1, diverges if p is less than or equal to 1, because equal to 1 it is a harmonic series. Now, this can be proved, it can be shown with the help of integral test. How? Let us consider that what the integral test says. If you look the integral test is this, that if you want to find the nature of this series, write down the corresponding integral f t, and then if the limit of this exists, then corresponding integral will converge. So, this will be taken like this. So, consider integral 1 to n dt over t to the power p. Consider this integral, because we want the sigma of this thing. So, f t is 1 by t. So, 1 by n p, and then this will give 1 minus 1 by p, 1 over n to the power p minus 1 for p different from 1. Now, if p is greater than 1, if p is strictly greater than 1, what happens? The limit of this as n tends to infinity 1 to n dt over t to the power p, this will, when p is greater than 1, this will remain positive, power is positive, it will go to 0, and we are getting basically 1 over p minus 1, a definite number. So, it converges, exist, instead of this exists. Okay? And if p is less than 1, this will go in the numerator. So, it will diverge. So, it will go to infinity, that is does not exist. It means the corresponding series, therefore, the series sigma 1 by t to the power p, instead of t we can write n to the power p, n to the power p, n is 1 to infinity, converges if p is greater than 1, diverges if p is less than 1. And for p equal to 1, obviously, it is a harmonic series. So, we can get this result quickly. Okay? So, that is what we are getting. Now, there are a few more tests which are known as the Ravi's test, and of course, the Ravi's test we will take up in next time. Then this. Okay, thank you very much. Thanks.